Okay, so let us see a little bit about how gradient descent works. So here, theta capital is the collection of all weights and biases of our network. So this can be very large. So there could be a lot of parameters, weights and biases. Some modern deep learning models, they have several 100 million parameters. Well, in any case, to do gradient descent, we initialize this theta with some small random values. This is how you do this actually matters. Usually this is done by the so-called Xavier initialization. Now you don't really have to understand very well how it works, but you just need to be aware that if you cannot just initialize everything with zeros, then your network is not going to train at all, right? So, and if you initialize it with some numbers that are too large, then it's not going to train very well either, right? So you need to choose kind of the good way, and the good way is known. So here it's just known. It's called Xavier initialization, and in Keras it's just in the library that we will use to train artificial neural networks. It's just the default, so you don't really have to worry too much about it. Then you choose this learning rate alpha, and then the first iteration is like this. So you compute the value. So this is the gradient. So the vector of derivatives of the loss function. So L is the loss function. And this is the vector of partial derivatives of the loss function with respect to all parameters. So if you have 100,000 parameters, then you just calculate the partial derivatives with respect to all these parameters. And then you evaluate it at the point theta 0, multiply by alpha, and that together, this is going to be theta 1. Then for theta 2, it's going to be the same thing, only you start from theta 1 and so on. So generally speaking, so theta t plus 1 is going to be theta t minus alpha times the derivative of the vector of partial derivatives of the loss function with respect to theta, evaluated at the point theta t. So this is the update rule for gradient descent. Now, even for simple logistic regression, so a neural network with no hidden layers, right? So there is one input layer and one-dimensional output layer and sigmoid activation. There could be some issues with this gradient descent. So let me just show you some plots, right? So this is the same problem. Age and the number of stings are our predictors, and the output is the probability of death from hornet stings. Now, this picture shows that the learning rate is when the learning rate is 10 to the minus 5, right? So this is the initial point. 0 is, well, actually, the vector here is three-dimensional. So there is beta 0, beta 1, beta 2. So the initial value is 1, 0, 0. Now I am not plotting beta 0 here. So I'm only plotting beta 1 and beta 2, well, because I just want a two-dimensional plot. And this is the trajectory of my gradient descent for a very small learning rate. So basically it goes like this. So first step, second step, third step, and so on, right? And we see that the final result is somewhere here, and the trajectory of the gradient descent looks nice and smooth. Now, this is what it looks like if I increased it 7 times. So the learning rate is now 7 times bigger. Now the trajectory of the gradient descent is not smooth anymore. This is simply because, the step is too large. So it doesn't look smooth. Another thing so notice that, but probably it means that our training was more successful because, so notice that, in the end of this trajectory, so it kind of turns to the right, right? And the reason for this being that maybe, this is kind of the point where it just stopped in the previous experiment, so with a smaller learning rate, because with a smaller learning rate, after that many steps, we just stop there. But now, if the learning rate is sufficiently large, then maybe we still have some more iterations to turn and to approximate our best optimal vector beta even a little bit better, right? So what I'm trying to say is that even though in the beginning, so the path, the trajectory of the gradient descent does not look very smooth, maybe it's not that bad, right? So let us see what's going to happen if we increase the learning rate even further, right? So now it's 2 times 10 to the minus 4. And now we see that it goes back and forth by large steps, and notice that the final result is quite different, right? So it's not really, it's quite far from what we saw previously. Yeah, so previously it was around 0.03, and now it's 0.1. I'm not sure what is better, but clearly it just wiggles too much, so it goes back and forth too much. And when we try to increase it even further, then it looks completely chaotic, right? So it goes back and forth, and of course, when it does this, we cannot be sure that the final result is really our answer, right? So because maybe if we just continue doing gradient descent, it's going to continue updating, and we will get a different answer there, right? So my point being is that with a too large learning rate, so the gradient descent may diverge or may not converge or may just be very chaotic and unstable, right? At the same time, if the learning rate is too small, then convergence is going to be slow. So it is a kind of tricky here to pick the optimal value of the learning rate. Now, for your information, for these partial derivatives with respect to weights and biases, they are calculated from layer L to layer 1. And so first we calculate partial derivatives of the loss function with respect to parameters in the output layer, then in layer L-1, then in layer L-2, and so on, right? So, and every time we do so by some clever matrix multiplication. And this process is called backpropagation. Now, in previous years, we used to teach backpropagation, but now I don't really want to do it anymore because first, this is not really a subject for this class. So this is a subject for a different topic, for a different discipline, for a different, module, for a different course. So if you are interested, then you just, go to the School of Computer Science and sign for a deep learning course or take a deep learning course online. So another problem with backpropagation is that it would take probably another week to explain it in all the details because it is quite technical, quite tedious, and doing questions on backpropagation on exams or midterm tests is just too tedious, right? So I can easily imagine that just doing one question on calculating partial derivatives of the loss function with respect to all the weights and biases would probably easily can take 30 or 40 minutes of your exam time. So this is why I decided not to include it in this year. But basically, it boils down to clever repeated matrix multiplication. Okay, so potential obstacles include multiple local minimum, or the fact that entries of the gradient vector can be of very different magnitude, right? So I don't know, some of these could be something like, 2000, and this could be something like, 0.1. And this could be a problem for gradient descent, right? So it means that in order to ensure convergence, we would have to decrease the learning rate, but then convergence is going to be slow. Now, so which is why in practice, instead of this plain vanilla gradient descent, so they're using some refined optimized version. Now here is the update rule. So all these optimizers, so-called optimizers, So they are basically just modified update rules for the gradient descent. So instead of just plain vanilla update rule that we are familiar with, so they use some slightly more complicated update rules. Now, this is the update rule for the Nesterov momentum. Again, I'm not going to test you on that. So it is just for your information that every optimizer has its own update rule. So, and this is the one for the Nesterov momentum. So the one for Adam optimizer is different. So, and then there are others. And the choice of the optimizer, it actually matters, not so much, but it matters. So, but it depends on the problem. So you cannot really know in advance which optimizer is going to be the best. So for some problem, it's going to be Adam. For some problem, it's going to be Nesterov momentum. For some other problems, it's going to be something else, and so on and so forth, right? So you probably you need to experiment a little bit to see, right? So this is unlike initialization. So the Xavier initialization is just always going to work, right? So, but the optimizer, so different problems, they call for different optimizers. But we never use the plain vanilla gradient descent in practice, right? So, and again, I'm telling it to you so that in the lab, you are familiar with the concept of optimizer. I'm not going to test you on optimizers, but you just need to know that there are different optimizers, and you need to know that sometimes you need to change to use a different optimizer to improve the training process, or to increase the speed of the training, or I don't know, improve the accuracy of the final model. Okay, so that's the end of part 9.